Hey everyone, this is Uday here from VCE Vanguard Coaching, and today I want to show you guys how you can solve an entire SAC during reading time. So today I really just want to emphasize the power of reading time and really how you can scaffold out answers for pretty much every single question in a SAC before you even start doing it. So I want to walk you guys through my thought process and how I sort of navigate reading time in order to answer questions optimally, okay? Now, basically, the first thing I want to say is that the whole point is not to actually find the answers of the questions, okay? Rather, you'll see that the main objective is to actually figure out the steps. And as long as you know the steps to solve the question, then you should be good to go when actually writing time begins, okay? So you'll kind of see that approach when we go through this practice SAC that I have over here, okay? Shout out to VCE Rocks for this. So as you can see here, we have a theme park, blah, blah, blah. They're investigating the design of a roller coaster. Cool. So we have a sketch here which shows different sections of the track. So really all I'm paying attention to here is we have like a linear section to begin with, then it's horizontal, and then we have a bunch of curves, but we'll figure that out as time progresses, okay? Now, the first thing that it tells us is that each section is a mathematical function, so we're probably gonna be dealing with piecewise functions here, okay? For safety purposes, all sections from section 2 need to be gapless and jointed smoothly. So automatically they're telling us that we're going to be dealing with smoothness and continuousness or continuity when we're dealing with these piecewise functions. So I'm just going to keep that in mind as we're answering the questions. When describing the domain, the first point is to be included, but the last point should be excluded. So that point will come in handy when we're writing these equations out. First and last points are to be included, whatever. That's just piecewise function writing. Okay? So, question 1. The roller coaster starts at the platform, which is 5 meters above the ground. Okay? So that's kind of where we're starting in this case, at the platform. Okay? And it will climb up to a height of 25 meters. So the highest point of that section 1, okay? I don't want to write on the paper because it's not allowed, but that highest point would be having a height of 25 meters. Okay? And the horizontal distance would be 16 meters. So automatically, it's basically saying we start at 0.5, then we move 16 to the right and 25 up. So you kind of have 2 points there automatically, okay? And they tell us what the x-axis and the y-axis is. First thing is determine the coordinates of the starting point and highest point. Well, we've actually already done that accidentally, so that's fine. But now we have part B. So basically it's saying find the equation of the track, okay? Or find the constants for this function here, and specify the restricted domain. So automatically what I'm thinking is, we have these 2 points. So what do I need to do? Well, all I need to do is calculate the gradient, which is m, using the gradient formula for 2 points. And then, using y equals mx plus c form, all I need to do is then sub in a point into that form and solve for plus c. So those are kind of the steps going in my head. I'm not trying to solve the question though otherwise, okay? And then finally, as for specifying the domain, well, they basically tell us that it starts at 0 and it's going to end, once you move 16 to the right. So that's already telling me what the domain would be in that case, probably 0 to 16, but that's fine, okay? Now part C, find the angle of this section to the horizontal line. So here, whenever you read angles and when it comes to, non-trig questions, you always want to think about how that links to the gradient. So there's a key formula, m equals tan theta. And so that's exactly the formula I would probably use in this case, right? So find the angle with respect to the horizontal line. They don't really specify what horizontal line. Perhaps they're talking about the platform here, or section 2, which is my guess. So let's just say that they're going for that obtuse angle. So we would probably use m equals tan theta, which would give us an acute angle, okay? And then we just do 180 minus that to get the obtuse angle. But of course, once we do this question with CAS, that will kind of confirm our suspicions as per whether we get an acute or an obtuse angle, okay? But we can manipulate that accordingly later on. And part D is basically saying, sketch this linear function that you found with the domain. Pretty easy, right? So as long as you have those basic skills, right, of finding the equation of the line, using m equals tan theta, and sketching a linear function, you'll see that it's actually not terribly difficult so far, okay? And part E, find the average speed. If the average speed during the train is 4.5 meters per second, how long does it take for the train to climb up to the top from the starting point, okay? So basically it's saying, what is the time given the fact that the speed is 4.5 meters per second, okay? To me, this is sounding like a distance, speed, time question. So we're starting at 0, 5, we're ending up at 16, 25, right? So what would that distance be between those 2 points? Because it's a linear track. We'd first of all want to find that distance, and then you divide that by the speed to pretty much get the time in this case. That's kind of the way I would go about solving this question for part E, okay? And there you go. As you can see, I'm not trying to find the answer, I'm just going through the steps in my head mentally, okay? Section 2 is now a flat track, so that's kind of a horizontal line in this case, okay? They're waffling a little bit. Flat section joins the slope with a sharp corner, okay? So it's not smooth in this case, it's just continuous, okay? But it's safe because it's not very fast, and the length of the flat section is 5 meters. So give a function describing the flat track. Well, it's a horizontal line, right? And I believe the height was 25, so it'd be y equals 25, or basically just y equals something, okay? And the length is 5 meters, so it's starting from 16 going all the way to 21, most likely, okay? Of course, like it's really just your domain would be 5 meters long. That's fine, okay? And now sketch a graph of that horizontal line. I think that's relatively straightforward. We can do that in writing time, okay? Now question 2. After the end of the ride in section 2, okay, the roller coaster train will accelerate and travel in a very fast way. Now there's no gap and it has to be smooth. So now we're really talking about the continuity and smoothness. Research shows that the shape of the track in section 3 can be modeled as a quadratic. It passes and finishes at 2618. So find the quadratic function in turning point form, okay? So what are my thoughts for this one? Well, first of all, they're telling us that now everything has to be smooth, okay? Meaning gradients at either end have to be the same. Well, if you look at section 2, that was a horizontal line with a gradient of 0. So if we're moving on to a quadratic, you can imagine that that very endpoint of the quadratic also needs to have a gradient of 0, okay? So therefore, what point on a quadratic has a gradient of 0? Hopefully you're thinking the turning point. So your turning point would basically just be that endpoint that we had found there at the end of 2, okay? So I believe we said that was like 21, 25, but that's fine, we can solve for that. That would give us the turning point. Then that wouldn't be enough to give us the full equation, right? Because you guys know it's like y equals a times x minus a squared plus k. So we would have found h and k, but we don't have a just yet, okay? So to solve for that final variable, well, as you can see, they've given us a third point, or a second point actually. So 26, 18. So we could just easily sub that into our equation and solve for a. That would give us the quadratic. So that's no problem there. Write the general equation in this form, you just expand it out with cas, that's fine. And then you scratch the quadratic. Nothing else really special in that case. Label the coordinates of the starting point and end point. It's really just classic graphing stuff, okay? Now, part D. Find the gradient of the track when passing through a position which has a horizontal distance of 24 meters, okay? So basically x is equal to 24. Give your answer in degrees, measured from the positive direction of the horizontal axis. Give your answer correct to 1 decimal place. Okay, so it's a little bit strange here because we're talking about gradient and angles. So I'd probably just hedge my bets and just write down both of them because why not? But let's talk about it. So find the gradient of the track when x is equal to 24, essentially. So you find your derivative, because your derivative gives you the gradient, and you sub in x equals 24, okay? That'll give you the gradient, okay? Now, the next thing that we'd have to do after that is we would now have to basically use m equals tan theta again, okay? So we would use m equals tan theta again, and that would give us an angle, okay? Of course, we have to be careful of whether it's a positive angle or a negative angle. So you always want to convert to decimal places just to be safe. But yeah, we could check that, and if it's a negative angle, then you could either manipulate it so that it's positive, or you could do like 180 minus it. I would need to see the graph here to really know what angle we're dealing with, okay? So that's something that we'll pay attention to for writing time. But we know it's basically just find derivative, sub x value in, use m equals tan theta, and then be careful. Those are your steps there, okay? And now it's saying when comparing the function f of x found in part A to y equals x squared, describe the sequence of transformations to obtain f of x. So my thoughts for this one is, the first thing I would personally like to do is I'd probably do the dilations and reflections, right? So remember there's kind of like that value A, if you look at part B. I want to take care of that first. So do whatever dilations and reflections are necessary, okay? And then after that, Of course, the turning point of y equals x squared itself is 0, 0. So I could just translate it so that the turning point becomes whatever the turning point was we found earlier. Okay, so basically just dilate and reflect, and then translate so that the turning points match up. Those are the steps in my head. Okay. Now it says use matrix form to describe the transformations. Matrix form is from an old study design. The current study design uses transformation equations. Okay, so basically we would just order it around, ax plus, I think, h, comma, by plus k. All my students sort of know that general form there. You can basically just write in everything. So you know your dilations and reflections. You can slot those in accordingly. And then the translations are like the h and k from that transformation equation. Okay, that's kind of just conceptual knowledge, even though some people don't always know it. But there's nothing really special there. Otherwise, you would just use that form. Okay. Now, section 4 passes through points. Okay, m, 18, 36, 24, and 40, 19. So part G is saying state the value of m. Okay. So it's section 4, which if I scroll up, it's kind of like that sort of, it's that sort of like dip and then up sort of dip and then peak type of shape, right? So it's told us 3 points. Now, one of them is m, 18, okay? Now, remember what we had spoken about earlier, right? Remember how we said that all of these functions are continuous now from section 2 onwards? Well, look at the quadratic. The quadratic finishes at the point 26, 18. And so basically this next question is probably relying on the fact that, hey, due to continuity, m would also have to equal to 26. So that's kind of what would be going through my head there. Okay, and now part H is saying, basically, this can be modeled by a cubic, find the values of A, B, C, and D, okay? And they basically told us the values, but we need to kind of show where these values come from, okay? Now, the whole idea is this. Whenever there's these questions where you need to solve for variables, I like to think about it like this. How many variables do we have? A, B, C, and D. We have 4 variables. So therefore, we probably need 4 simultaneous equations to solve for this question, okay? Now, we have 3 points up above. That would actually give you 3 of the 4 simultaneous equations. For example, g of 36 would equal to 24, g of 40 would equal to 19, so on and so forth, okay? So where does the 4th one come from? Well, the 4th one, once again, comes from the fact that everything needs to be smooth, right? So you need to start thinking about all the characteristics of the question. So if you have all of the points here, we have that idea about continuity. Now we also need to take into account the smoothness. So in my head, that final equation would be g dash of 26, because that's the left endpoint, right? G dash of 26, which is for section 4, which would equal to f dash of 26. Remember, f is the quadratic, so the gradients on either side would have to be equal, okay? And so that's how you can figure out your 4th equation. And so with those 4 equations, you just solve simultaneously on CAS, you would get your answers. So relatively straightforward in my opinion. And that's sort of why they reminded you as well, the tracks join smoothly, okay? So that's where the 4th simultaneous equation would come from, okay? So in the end, after that, you would then have your full equation of the cubic, okay? Part of that is saying find the max and minimum height, okay? So literally you can just use f min and f max, that's fine, okay? Find the value of n, where section 4 and 5 meet, okay? Which is 41, n, okay? So 41, n is a point which lies on the roller coaster, okay? That's the very right endpoint of section 4. So you can imagine I would just sub in x equals 41 to get the y coordinate, which would be n. So that's fine, okay? Specify the domain and range of g of x, which is this roller coaster, okay? Well, first of all, we know that it starts at 26, okay? Because that's where the quadratic ended. And it ends at 41. So your domain would be 26 to 41, okay? So it's really just graphically understanding the information that they've told us. And the range, well, we're told what the minimum and maximum height are, or we would have found that using CAS. So your minimum would be the bottom end of the range, maximum would be the upper end of the range, okay? So really, you just use your answer from the previous part to answer that, okay? Sketch the graph within the domain. You can just use CAS and make sure you label all your points. And of course, be careful with the endpoint stuff, like which one you include versus which one you exclude, as I had mentioned prior, okay? Cool. All right, now we're at question 3, okay? Now, obviously, you might be saying at this stage of the video, you might be like, okay, well, you're taking a lot of time here, though. You don't have that much time in reading time, okay? I want to let you guys know that, of course, I'm verbalizing my thoughts here, right? So that's why it's taking a little bit longer, and of course I have to explain it a little bit to you guys. But if you guys can actually understand how to solve each of these questions, oftentimes you can just read the keywords like maximum and minimum, okay, max turning point, minimum turning point, that's all I need to find, and you move on. So you can imagine that even when I'm explaining these questions, a lot of these things, if you know the underlying calculations, zooming through it is really easy. So I just want you guys to keep that in mind, okay? Now, moving on to question 3, section 5 of the track, okay? So now we have this sort of last part here that we haven't looked at yet, okay? It's the last one to be discussed by Brody, okay? And that can be modeled by a hyperbolic function. So if section 5 ends at the position where it is 3 meters above the ground, in other words, h is equal to 3, find the horizontal distance. In other words, find the x value. So you just solve h of x equals 3, and you get your x value. I think that's straightforward, okay? According to scientific research, it can only be stopped when the gradient is less than 5 degrees. So once again, they're kind of making that link between gradient and the degrees. So there's going to be some m equals tan theta business going on here, okay? So if the cart needs to stop safely at the endpoint of section 5, then we will have to extend the track. So how much further in horizontal axis does this section need to be extended? Okay, so this one's a little bit of a deeper question. So I'm going to kind of explain my thought process for this one, okay? So what they're saying here is we have this hyperbola, right? And at this stage, what we've drawn, right, the graph is still a little bit too steep for our liking, okay? Because we want this roller coaster to be very safe. So what they're saying is, you can imagine that if we were to continue on with this hyperbola, it would become flatter and flatter, because that's just an aspect of hyperbolas, right? So basically we're saying, let's extend it further, because now our hyperbola is going to get flatter and flatter, okay? And as it gets flatter and flatter, then we can kind of end it a little bit later on, because now it's going to be safer to stop, okay? So what we want to figure out is, well, when do we stop it? And we're going to be stopping it when that angle that we form is only 5 degrees, okay? So you can imagine that that's where m equals tan of theta would come into play, okay? Now the first thing I want to keep in mind here, and this is of course something that we would figure out further with CAS, but 5 degrees doesn't appear to be the angle with the positive x-axis. It seems to be more so like the angle underneath the x-axis, essentially, okay? So you'd have to be a little bit careful here. I'd probably be using m equals tan of negative 5 degrees, to be honest with you, because we'd expect the gradient to be negative, okay? Of course, you can kind of work around that yourselves, with your calculator, but just be careful, right? M should be a negative value. That's the first thing, okay? Now the second thing, because, you can see the gradient of your hyperbola is negative, okay? Now with that in mind, what would be the steps? Well, we're talking about the gradient and we're talking about the angle. So first thing that I would do is I would take the derivative of this hyperbola, okay? Because that's going to give us the formula for our gradient. Now the next thing is we want to figure out what is our desired gradient. So m should equal to tan of negative 5 degrees, whatever that value would be. Now the next thing is that you just solve for when your derivative or your gradient is equal to tan of negative 5 degrees, okay? And that will give you the x value, okay? And basically, with that x value, that's where we can restrict the hyperbola, okay? Because that's basically the x value for which your hyperbola is now making less than 5 degrees to the ground level, okay? So that's kind of the thought process for part B, but that's kind of one you would flag in your head, like, hey, let's be a little bit extra careful with this one, because there's some weird calculations going on, okay? All right, and now we're kind of reaching like the last couple of questions here. So now basically they've kind of given up on the roller coasters, and now they're saying we have these two simultaneous equations. Okay, if there's no real solution, find the values of a and b. Okay, so this is like a very standard question type. Okay, really it's just saying you have two equations. If there's no real solution between them, well, what's going on? Well, if you imagine two lines which have no real solution, that means that they're parallel. Parallel lines have the same gradient, but different y-intercepts, okay? So what we could do is we could rearrange both of these equations into y equals mx plus c form. Then what we can do is we can make their gradients equal to each other, okay? And that will give us one simultaneous equation, because remember, there's two variables here. And then the next thing that we can do after that is we can equate, we can make the y-intercepts and see when they're equal versus not equal to each other, okay? So usually you'll get you can kind of compare, well, what happens when the y-intercepts are different to each other, okay? And that'll kind of give us the second thing to analyze, okay? And then we can sort of solve those two equations, or we can just analyze them, and based upon that, we'll see what values of a and b work, okay? But really the main idea is same gradient, different y-intercepts, okay? Now, if there's a unique solution, that's really what part B is saying now, okay? If there's a unique solution, that's basically just saying your two lines would intersect once, meaning that pretty much they just have different gradients. So as long as your two gradients are not equal to each other, okay, then you would have a unique solution, okay? And finally, when there's infinite solutions, my thoughts here, the same gradient, but also the same y-intercept. So those are going to be the two things that I would solve and equate, but I'm not going to do much further during reading time, okay? Because I don't want to rearrange all of that in my head, okay? And now we move on to question 5, which is our final question here. So define functions p of x. So you have a parabola, which has a restricted domain. So you have the right half of a parabola, and you have a rectangular hyperbola, which is not really restricted. So give the rule and domain of p inverse. So basically, you're just finding the inverse of a parabola, so that would be a square root function, okay? And the domain of p inverse would be the range of p, which in this case, I can deduce it's 1 to infinity, but like I said, you don't really need to do that calculation at this stage. You'll just get back to it later, okay? Part B, sketch p and p inverse. All you need to be careful with in this case is remember the domain restriction on p of x, and remember that inverses are reflections of each other in the line of y equals x. You remember those two things, you should be good to go, okay? Part C, show that p of q of x is not defined. So now we're starting to talk about composite functions, okay? So when are composite functions not defined? Well, generally speaking, that's when the range of q does not fit inside of the domain of p, right? So that's kind of a conceptual piece of knowledge that you need to know. So all we would do is we figure out the domain and range of both p of x and q of x, okay? And then we just need to show the fact that, hey, the range of q of x does not fit into p of x, okay? So those are the steps that we would do. Obviously, we would execute on those in reading time because, yeah, we can't really be bothered trying to do all of that right now, okay, in reading time. So part D, restricted domain of q so that p of q of x would be defined, okay, and then state the rule. So we know we've shown previously that it does not exist. Now, how can we make it exist? Well, basically, the range of q of x, right, has to fit into the domain of p, which is 2 to infinity, right, as you can sort of see over here. So basically, we would just solve, well, hey, when is q of x between 2 and infinity? Okay, so that's kind of another standard problem question, which you just need to know how to solve in this case, okay? But yeah, when is q of x greater than or equal to 2? Solve for x, that'll give you the restricted domain. And as for stating the rule, you'll literally just sub q of x into p of x. It's not really too hard there, okay? So those are my thoughts for that one. And part E, which is our very last question here, is just sketch the composite function on the axes provided below, okay? So quite literally, you could just take has and you could just sub it in because it'd be a little bit weird because you have like, well, it wouldn't be too hard, but you'd have like a rectangular hyperbola squared essentially, okay? So you could just use cas to kind of sketch that and just be careful with your domain and stuff like that. But we'll get to the calculations in writing time, okay? And there you go. That is actually the entire SAC that we've pretty much just deduced the steps for in reading time, okay? So hopefully you guys now have a better understanding of how we approach questions during reading time. We're not trying to solve them manually, but we want to figure out, hey, what equations or what pieces of information can I sort of link or utilize to solve for different variables, okay? So it's really about aggregating all of that information and understanding the steps, and then in writing time, we can execute and ultimately save a lot of time, okay? So I hope you guys got a lot of use from this video, and hopefully you can kind of emulate the things that I would do in a SAC as well. Anyways, guys, I'll catch you guys around later for another video. Please like, subscribe, comment, follow, do all that good stuff, and I'll see you guys next time.